Good morning to everybody. In 1 minute, we begin.
Yeah.
Dear all, so shall we start? The last day of our conference, and I will be the chairman of the first two sessions today. And it's my great pleasure to announce the first invited talk of this day of the conference. It will be given by Professor David Brook from San Jose State University, and he's going to talk on diverse magnetic properties in transition metal coordination compounds. Please, David, the screen is yours.
Okay, thank you for the introduction. Hopefully we can see. Hold on, I gotta
Yes, everything is perfect. Thank you.
Okay, so let me see if I can find a little pointer here. Here we go. Okay, so there we go. Okay, so what we've been studying for the past 10 years or at least is we're looking at coordination chemistry of there we go, coordination chemistry of 6-oxoverdazels, and so this is a typical 6-oxoverdazel. I'm lost in Windows. 6-oxoverdazels have their heterocyclic free radicals. So we have an unpaired electron. It's drawn on the nitrogen here. I've got my annotation thing back. Here we go. Okay. So it's drawn on the nitrogen here, but in reality, it's delocalized over all 4 nitrogen atoms. The singly occupied molecular orbital looks something like this. But what's interesting about them is that the nitrogen that bears most of the spin density of these 2 nitrogens also can coordinate transition metals, and so we're using them to look at interesting and see we can develop interesting magnetic materials and magnetic structures. And if I can, I'm having problems advancing slides here. Hold on a second. Here we go. And there's lots of examples of coordination compounds with polypyridine ligands, such as terpyridine. You combine it with a transition metal, and you can form structures like this, and you can form all sorts of complicated self-assembled systems. So the thought we had when we started this research is can we replace some of these transition metal structures, some of these pyridines with free radicals, and generate some interesting magnetic structures. So not only do our 6-oxoverdazels have this unpaired electron, but they're also redox active as well, which also adds to what we can do with these. So as I said before, we've got a coordination site, we've got these 2 nitrogens, we can change the substituents on the structure, and we also have this interesting probe of the electronic structure that is the stretching frequency of the carbon-oxygen double bond. So if it's reduced, which is way over on the right, you can see a lot lower stretching frequency than if it's completely oxidized. And so we have a nice system both to probe the electronic structure and also generate interesting magnetic structures. So this is our building block. It's not always as straightforward as we started. So the main problem with these is that verdazels themselves, with all those nitrogens, they're not very basic. And so there are verdazole coordination compounds, but all of them have a chelating substituent that helps bind any metal ions. And the alkyl groups that we already have on there interfere with the octahedral coordination geometry. So we're not the only research group who does this. Robin Hicks published this structure way back in 2000. And so we got a verdazyl here that's coordinated to a nickel in the middle. So it's a terpyridine-like structure, and you see very strong ferromagnetic exchange. But one of the interesting features is this methyl group up here. You can see it's actually interacting with the perpendicular ligand, and that results in a very long or relatively long nickel free radical bond. It's actually the longest metal ligand distance in the structure. In fact, I got bond distances up here. So you can see that the nickel verdazyl bond length is 2.2 angstroms, whereas the other two bonds to the other two pyridine rings are 2 and 2.1 angstroms. And so, you know, if you're pushing away your free radical, you're going to limit the amount of limit the amount of magnetic interaction you can get. So what we set out to do is, instead of starting with this terpyridine with the verdazyl at the end, is, well, what if we can do this? If we can replace one of these methyl groups with a pyridine ring, then instead of getting in the way, now this pyridine can also coordinate the metal ion, and it becomes part of the solution rather than being part of the problem. In the process, we actually replaced this methyl group with an isopropyl group. It turns out the synthesis of this ligand with an isopropyl is a little easier, though it's not a straightforward synthesis. I'm not going to go into it now because I don't have time. But anyway, so what we're going to talk about today is the coordination chemistry of this ligand with first-order transition metals. So the first thing we looked at was nickel. A lot of the literature of coordination chemistry of free radicals, there's some sort of standard experiments. If you do a coordination with nickel, you expect ferromagnetic exchange. You do manganese, you expect antiferromagnetic exchange. And so that's what we started off doing. We looked at nickel. We took our free radical. We give it this abbreviation dipyridyl verdazyl. It's an S equals half system. We added nickel, and we get a very nice crystal structure. Very nice crystalline material. It's deep red, and here we have the verdazyl. Now it has isopropyl groups coordinated to the nickel, and we've reduced the nickel verdazyl distance by almost 0.2 angstroms, which makes a big difference, because now if you look at the magnetic properties, which we just skipped ahead to, you can see a plot of chi-T versus T. Essentially there's one state that's populated. There's the S equals 2 ground state, where the two free radicals and the two unpaired electrons of nickel are ferromagnetically coupled very strongly, and there's no significant deviation in chi-T from the value of 3 until you get up to like 200 Kelvin or so. And if you model this interaction, you can come up with coupling constants, exchange constants. There's two constants. You can have the metal radical exchange, you can have the radical exchange through the metal. When you do the modeling, those two numbers are very strongly correlated, so you really can't get a good value on both of them, except they're both, whatever it is, it's strongly ferromagnetic. So I'm going to depict the electronic structure like this. Here's our nickel with the nickel d orbitals. We've got 2 unpaired electrons on the nickel, and then we have 2 ferromagnetic coupled ligands. And this is consistent with normal orbital overlap expectations. So we have, the nickel is in a sigma type orbital. The nickel unpaired electrons, the pi electrons of the radical don't overlap, and so we get ferromagnetic exchange. So this is pretty straightforward, and we published this, like 10 years ago now. But then we started looking at other transition metals. Does this all sort of make sense? So we can look at manganese as well. The synthesis is a little different. We're actually starting from a reduced version. So we're not starting with a free radical here, but if you combine this leucoverdazyl, as we call it, with manganese triflate in oxygen, it actually spontaneously oxidizes to the diradical. We've got a crystal structure of that. And this, as is typical for manganese coordination to free radicals, the exchange is antiferromagnetic. So now we have, this is chi-T versus T again. And you can see that as you increase the temperature, chi-T is increasing as you're populating higher spin states. Manganese is a D5 system. You have 5 unpaired electrons, and they're coupled antiferromagnetically with the 2 ligands, giving you an S equals 3/2 ground state, which this is consistent with. And again, this is consistent with orbital overlap, because 3 of these electrons on the manganese are in a pi-type orbital, and you get anti-ferromagnetic exchange. So it's all makes sense. It's relatively straightforward. The one remarkable thing about these is you'll notice that the values of exchange are very strong. And we attribute that a lot to the very short metal radical distances because the radical is in the middle of the ligand. It's typical for actually terpyridine systems that the central pyridine bond distance is a lot shorter than the other two, and this is consistent with that. And zinc, you know, continuing the series, series of the boring ones. Zinc we can do essentially the same thing, and we get a zinc complex. It's a diradical, but in this case, the two radical ligands actually really don't interact at all. There's no mediation by the zinc, which actually surprised us. So like the radical exchange is 0 reciprocal centimeters, and I've missed out some electrons here. My apologies. Zinc, of course, is a D10 system, and I've only put 6 electrons in, so my apologies for that one. But essentially, the two unpaired electrons on the ligands just completely independent in the system. So yeah, we have strong ferromagnetic exchange, we have strong anti-ferromagnetic exchange, we have no exchange. These are all pretty straightforward. One of the things that's kind of interesting here, though, with the zinc is that we actually made this in a different way. We took the leucovodazole we saw with the manganese, and if you take that and combine it with the zinc and deprotonate it, then you can actually get a diamagnetic compound where the two ligands are anionic, and then you can oxidize it with silver to give the diradical. And so that tells you that the ligands are still redox active when bound to the metal center. And so that actually leads to some far more interesting chemistry. So this is an example of the, for the zinc itself, we can do, this is a cyclic voltammogram for the zinc complex, and you can see the two sequential reductions of each ligand. They're relatively close together, which is consistent with the ligands not interacting too strongly, or one ligand is reduced pretty soon after the other one. So the interaction like mediated by zinc is pretty weak. But you know, zinc, manganese, and nickel are not the only transition metals. And so we started looking at copper is one that's also been studied a lot. The exchange interactions are usually pretty straightforward. Copper has one d electron that's in a sigma type orbital, so we'd expect ferromagnetic exchange. But it turns out that in a lot of cases with copper, because the coordination geometry is so flexible, it's not as straightforward as that. So we wanted to see what would happen with copper. So again, so we can take our ligand, our leucovodazole in this case again, react it with copper triflate, deprotonate the ligand with triethylamine in methanol, and we get a very nice just copper 2 complex with 2 anionic ligands, and it has this ESR spectrum, which clearly indicates that it is actually copper 2, the unpaired electron is on copper. It's not, there's no radical, no organic radical in this system. But again, we can oxidize it. In this case, if we oxidize with silver hexafluorophosphate, in fact, excess silver hexafluorophosphate does nothing. We can oxidize one of the ligands to give a mixed system. One ligand is anionic, and one is a radical. If we want to oxidize both ligands, we have to give it a bit bigger kick, and it works out. We can actually do this quite nicely with nitrosonium hexafluorophosphate, and we can actually get the diradical. So we have crystal structures of these, and this is where it starts to get interesting, because we haven't really seen yet in this presentation examples of reduced ligands. So if we have the monocationic system, you can see clearly that we have one of these ligands is a free radical. It's not so clear that this one is planar, but it's quite clear that this ligand on the right-hand side with the monocation is not. This is actually an anionic ligand. The tetrazane ring in these anionic ligands is actually deviates from planarity significantly. It's puckered. That makes sense, because if you do an electron count on this thing, it's like an 8-pi electron system, so it's anti-aromatic. And so when you oxidize one ligand, one of these is a free radical, and one of these is an anion. If we oxidize both of them, then we can see both ligands are pretty planar, and so we have two radical ligands. You can also see this in the infrared spectrum. So in the infrared spectrum, we have for the radical ligands. So let me start off with the fully reduced system. The anionic ligands is this blue trace. There's one carbonyl stretch around 1668 reciprocal centimeters. which is consistent with the anionic ligand. When we oxidize one ligand, we get this red trace, which has two carbonyl stretches, one for each ligand. One's at 1668, more or less. One's at 1724 for the free radical. And then we oxidize both of them, and we get one peak for just the free radical ligands. So in terms of chemistry, this is nothing remarkable, but we'll see that it turns out to be a very useful reference point. But I would like to talk briefly about the magnetism of these systems. So again, we see very strong exchange. In this case, the exchange is ferromagnetic again. So for the cation, we have one unpaired electron on copper. We have one unpaired electron on one of the ligands. They couple ferromagnetically, so we have an S equals 1 ground state. And fitting this gives a very strong ferromagnetic exchange, 260 odd reciprocal centimeters. And when we have two free radicals, then we have ferromagnetic exchange all around. Again, metal radical exchange 350. Again, these parameters they're correlated, so the actual values is not so much as significant as the fact that they are both large and ferromagnetic. And we have a S equals 3/2 ground state. I'd like to actually point out and contrast the bipyridine substituted Vedazyl that Robin Hicks reported. It's quite different in this regard. He reported a copper-2 complex of that. And in that case, the exchange was really quite weak. It was like an order of magnitude smaller than this. And I think it was mostly anti-ferromagnetic. So just putting the free radical in a slightly different position in the ligand actually makes a pretty big difference. But there's other transition metals as well. And this is where it starts to get really interesting, because there's very little done with free radicals coordinated to iron. So when we started looking at this was kind of new territory, and we found some very interesting, at least I think very interesting results. So again, similar sort of strategy for synthesis. It turns out it's a lot easier to start with this leucovedazyl than the free radical itself. The uncoordinated free radical, while the coordination compounds are very stable, the uncoordinated free radical, this particular free radical, tends to decompose slowly. It's not the easiest thing to handle, whereas the leuco radical, this diamagnetic species, actually is crystalline. It's stable, and so it's a lot more useful starting point. But we can react that with iron-3 salts. In this case, it's iron sulfate and methanol and water. Obviously, there's some proton transfer and other things involved. And we get what I'm depicting here as iron-2 coordinated to one radical and one anion. And we'll talk about exactly what the electronic structure of that is in a minute. Essentially, we have a molecule that has the same structure overall. It has one positive charge. And again, we can oxidize this again with our favorite oxidizing agent, silver hexafluorophosphate. We can oxidize this remaining radical to give a diradical system. Now, what's interesting about these? Well, let's look at the crystal structures first of all. Again, so this is the dication. So this is a free radical here. This is a free radical. This is iron-2. The bond lengths here are all relatively short, which is consistent with low spin iron-2. The cation itself, the bonds, the metal ligand bonds, I don't have the numbers up here, but they elongate, which is consistent with a low spin to high spin transition in iron. And so now we get some interesting magnetic effects because of that, the fact that iron can be low spin or high spin. We start to interact with the ligand, things get a lot more interesting. We can see the ligands still are pretty flat. They're not nearly as puckered or as they were with the clearly anionic ligands in the copper system. So it becomes an interesting question: is what is the exact electronic configuration of this? What do we call this? Magnetic properties should help. So we have here this is the cation, and you can see that it looks like chi-T is 4.2 or so. This is consistent with a S equals 5/2 ground state. And for the dication, chi-T increases slowly to about 1 before it drops off at low temperature, which is consistent with a triplet or S equals 1 ground state. And we can fit this to a coupling constant of ferromagnetic coupling. There really is no fit for this up here. There's a line plotted in here. I wouldn't ascribe much meaning to it. Essentially, chi-T is constant So we have so whatever the ground state is, that is the only populated electronic state at room temperature, which is pretty remarkable. So how do we describe these things? The dication, we saw the bond lengths are consistent with low spin ion 2, which makes sense. We have the d orbitals all populated, or the d pi orbitals all populated, and then we have 2 unpaired electrons. And unlike the zinc system, when these things didn't couple at all, these are coupling quite strongly. So there's some extra interaction that's mediated by the ion, which is interesting. When we add an electron to form the cation, we can draw it like this. We can think of it as high spin ion 2 coordinated to an anion and a free radical. But we could also think of it as ion 3 coordinated to 2 anions, and we have the question of which is it. Both of them would be S equals 5 halves systems. This one intuitively makes, it seems pretty straightforward. It's like, well, it's high spin ion 3, it's going to be S equals 5 halves. That's consistent with this invariant magnetic value of chi t. But this is not consistent with the molecular geometry, because this would be anionic ligands. We would expect them to be non-planar, and they're clearly pretty close to planar. So how else do we look at this? We can take a look at the infrared spectrum. I got some ideas. We've got some redox chemistry going on here. I'm not going to worry about the potentials up here, but you can see that again. So for the dicationic system, we have a molecular carbon-oxygen double bond stretch at 1724, which is consistent with 2 radicals. For the fully reduced system, which we haven't actually isolated, but we actually generated by reduction with cobaltocene, you can see a single carbonyl stretch at 1667, which is consistent with what we saw with fully reduced ligands before. But for the intermediate system, which on paper at least has 1 reduced ligand and 1 radical ligand, doesn't have 2 different carbonyl stretches. There's only this one blue line. There's probably a little contamination here, but there's only 1 carbonyl stretch at 1689 reciprocal centimeters, which tells you that both of these ligands are identical. So we have kind of an interesting system where we've reduced what appears to be the ligands, because it's still ion 2, but that extra electron is delocalized across the entire molecule, across both perpendicular ligands. That sounds a little unintuitive. How can the extra electron be delocalized across 2 ligands that are actually 90 degrees to each other? And the trick is that they're not totally symmetric. So if you look at the ESR spectrum of this ligand, you can see that the coupling, the hyperfine coupling to this nitrogen is slightly different from this. So there's an asymmetry in the spin distribution, and that results in the possibility of an interaction with 1 d orbital here that will actually overlap with the spin density on these 2 nitrogens both at the same time. So we can explain that delocalization, and it also provides an interesting explanation of why we have an S equals 5 halves ground state, because you would expect, with partly occupied d pi orbitals, the xz, xy, yz, you might expect antiferromagnetic exchange the way we saw with manganese, but clearly this is strongly ferromagnetic. And you can argue the delocalization essentially results in, so if you think about the way I've drawn it here, is we have these red electrons in red essentially are delocalized across both ligands and the d orbitals. And by delocalizing them, they essentially align the remaining unpaired electrons on ion. You can think of it as sort of resonance mechanism that results in what this very high spin ground, a high spin ground state, even though you might not expect, based on just purely overlap, ferromagnetic exchange. Cobalt, the last of our first row transition metals that we'll finish up with. And again, similar synthetic strategy, start with cobalt-2, react with, so cobalt triflate, again with our ligand. And in this case, it again gets oxidized with oxygen. And we actually isolate a very nice deep green diamagnetic species, which is clearly a cobalt-3 system with dianionic ligands. So that it's not essentially that interesting, but we can oxidize it with, again, silver hexafluorophosphate by 1 electron. And now we have what I've drawn here again. The state is not necessarily this. If we oxidize 1 ligand, we would expect 1 free radical, 1 anion, and cobalt 3. But so this is the actual structure of the diamagnetic system. You can see again we have anionic ligands that are not planar. You can see one of them. The other one is also not planar, but we're looking at it in the other direction, so it's not obvious. It's a S equals 0 ground state, anionic ligands, low spin cobalt 3+. We oxidize it with 1 electron, and we go from low spin cobalt 3 to high spin cobalt 2. And we can tell that because now the ligands are both planar. And I don't know if I put this in here, but again, you see a change in the carbon-oxygen double bond stretching frequency consistent with these being radical ligands. Yeah, in fact, here it is here. So this black line, this is the dianionic system. It's a little shifted from the vibrational frequency for the other anions, but the idea is still the same. We oxidize it, we have 2 radicals that, and so it's clearly 1724 reciprocal centimeters. And it actually has a S equals 3/2 ground state, which is it's still not clear quite how that arises. There are other systems that have a similar, have the same electronic configuration. But that's not what I want to get into right now. What I want to point out is what's interesting is when you dissolve this material, this crystalline material in acetonitrile or acetone, now you have 2 carbonyl stretches. So we're going from 1 ligand environment to 2 different ligand environments. And if you look at the magnetic susceptibility, it drops dramatically, but we appear to have some excitation. In fact, we have an equilibrium between S equals half and an S equals 3/2 system. We have a valence tautomer. So essentially what we've gone from is like high spin cobalt 2 to low spin cobalt, high spin cobalt 2 with 2 radical ligands to low spin cobalt 3 with 1 radical ligand. And the high spin state is the excited state. I'm getting low on time here, so let me finish this up. This is the equilibrium here, but to point this out quickly, what's interesting is that the crystal lattice is clearly trapping a high spin state. And so we thought if we change the anion, we may be able to manipulate that. And in fact, so we switch hexafluorophosphate for hexafluoroantimonate, and now we have 2 carbonyl stretches. We have a crystal structure where we actually have a planar ligand and we have a puckered ligand. So now we have 2 different ligand environments and not such detailed magnetic data, but we have a similar magnetic properties in the solid as we did in solution. So this is the hexafluorophosphate, this is the hexafluoroantimonate, and this is in solution. So we have a nice example of valence tautomerism. There's a few other interesting quirks. So when you crystallize some of these systems, you can actually trap metastable states that have both ligand environments, and some of these show some interesting hysteresis in magnetism, but the states are not very well defined and they tend to decay. So we can isolate this blue thing here, and then after a month or two, that extra carbonyl stretch has gone away, as has the hysteresis. So there's some interesting things here, but we're still investigating this. And this just kind of points out that manganese, nickel, and zinc, they have redox chemistry that's all pretty similar, the 2 ligand, but the copper, cobalt, and iron are a little different. And so there's some sort of interesting trends, but I'm running out of time. So I would like to acknowledge a whole pile of students and collaborators. Most recently, Sebastian Stoyan, who's been, the University of Idaho has been helping out with Mossbauer and high field ESR spectra, which has been very useful. Lots and lots of students have worked on this for many years, and funding has come from National Science Foundation, San Jose State University, ACSPRF, Department of Defense in the US, and C-Superb is actually a California State University funding agency. And I would be happy to answer any questions you have.
Thank you very much for the inspiring talk. We have one question already from Kira Vostrikova.
Okay, thank you very much for your very interesting talk. But I have some unclearly situation because for your complexes were presented only chi-t versus T plots without presentation magnetization, and for this reason it is not possible to know what is about the ground spin ground states in these complexes. And I would like to if you can clarify this situation, and also for studying such systems, it's also to obtain very useful information. It is better to check also electronic spectra, because you could see charge transfer in these systems. I would like to know if there are some compounds with charge transfer, especially for one radical, one anion systems.
Those are really good questions. So in terms of the magnetization studies, we have done some, and it's I just haven't, there's limited time to present all the data, but all the data we have is consistent with the ground states that I presented. But I mean, it is a good point that the magnetization studies make things more complete. The charge transfer is actually a really good point. So for the one where it's most obvious, I'm not sure if I have that spectra, if I can. So for the ion systems, there is actually a very strong charge, what we call an intraligand charge transfer band that's in the near IR. It's like around 1,000 nanometers or so. And so I mean, it's there, and there's also but it's sort of complicated because there's also metal ligand charge transfer bands as well. For the three simple cases for zinc, for manganese, and for nickel, the electronic spectra are almost identical, and so essentially what you're looking there is purely ligand-based transitions. But it does get a lot more complicated with the other systems. As I said, there is clearly intraligand charge transfer in the ion systems. The cobalt, we really haven't dug into that one yet. And I think the copper system, there is probably an intraligand charge transfer band there, probably in the infrared, but that data is actually, the presentation is not data in chronological order. The copper system is actually some of the newest data we have, and we haven't actually got around to looking at that yet. But that's looking for intraligand charge transfer bands is something that we really want to do. We've got more work to do on those things. So
okay, I'll wait for full publication.
okay.
Yeah, we are actually quite behind of time. David,
Sorry,
no, it's no problem, and thank you very much for doing it almost in the midnight of your time.
Yeah.
I see there is a question from David to David. So may I ask you to do it via chat, okay, so that we move to the next talk, right, because we are something like 8 minutes behind. And thank you once again, David, for wonderful presentation. And the next talk will be given by Kenji Sugisaki from Osaka City University, who is an expert in computational chemistry applied to molecular magnetism and quantum computing. So please, Kenji, the screen is yours.
Okay, thank you very much. So first of all, I would like to thank the organizers for giving me chance to present my recent work. So today I'm going to talk about the development of quantum algorithm for quantum chemistry problems, especially for the data calculation of exchange coupling parameter J. And the result I'm going to present is published in Chemical Science Journal, shown here. And I'm going to talk about how quantum computers can perform the computation that is impossible on classical computers. So developing such quantum algorithms is very important to make quantum computers really useful for chemistry and physics applications. So let's think about the biological molecule. Assume that you have a new biological molecule. And the first thing I think that you want to check is the ground state, spin state is high spin or low spin. So you can measure the magnetic susceptibility, or if the compound is either active, and you can, if you are lucky to observe the forbidden transition, you can check the temperature dependence of the ESR forbidden transition. Another approach is, of course, using a quantum chemical calculation. And in any cases, we usually analyze the spin state energy gap by using a Heisenberg Hamiltonian as shown here. And this Jij is exchange coupling parameter. And this is Heisenberg Hamiltonian. As shown, let us think about the two spin system as the simplest cases. The possible spin states are spin singlet or triple states. An eigenvalue of the Heisenberg Hamiltonian are shown here. So the energy gap between two spin states is equal to J. And if J is positive, it means that triple spin state is the lowest energy. And the two spins are coupled ferromagnetic manner. And if J is negative, the single state is the lowest spin state, and two spins are anti-ferromagnetically coupled. If we measure the magnetic susceptibility, you can fix the magnetic susceptibility by using a brain power model, which is also known as a single trapper model. So we can determine the J bar by using a simulation of the magnetic susceptibility. Of course, in quantum chemistry, we usually use the Brook symmetric DFT to calculate the exchange coupling parameter. In the Brook symmetric DFT, the triple state, high spin state is well approximated by a single configuration as shown here, but the opposite singular state cannot be approximated by a single configuration. So instead, we use a linear combination of the high spin and low spin state to generate a single configuration, which is known as Brown symmetry wave function. By calculating the total energy of the Brook symmetry and high spin state and XL operators, XL values, and substituting these values to the well-known Yamaguchi equation, which extends the J value. So in quantum chemical calculation, so we have to calculate the high spin and low spin state individually to obtain the exchange coupling parameter J. But the situation will change if we can use a quantum computer. So what is quantum computers? There's several talks already in the conference discussion on the quantum computer. But anyway, if we define a quantum computer by a single sentence, it is a computer that operates according to quantum mechanical principles. So rather different is used in quantum computer. We use qubits as a mirror unit of information, and some problems can be solved exponentially faster compared with the classical computers. So quantum computer is not universal, basically. So the exponential acceleration, the problem that can be accelerated exponentially by using quantum computer is very limited. But the development of such quantum algorithm is very important. And actually, 2 years ago, Google Group reported that some problem which takes about 10,000 years on the supercomputer Sami can be solved by using quantum computer within 200 seconds. So this is one of the demonstrations of the quantum supremacy. So quantum bit, in the classical computer, we use a bit. So bit can be state either 1 or 0. So or it's just on or off state. But in quantum computer, we can use a qubit, which can be arbitrary superposition on 0 and 1 states. So quantum state can be represented as shown here. And we can use a box sphere to represent 1 qubit quantum state, shown here. So I would like to explain the mechanism of the quantum chemical calculations on quantum computer. And here I explain the mechanism of quantum phase estimation algorithm, which is used to calculate the Fuchsian energy on quantum computer. The mechanism of quantum phase estimation is very simple, actually. Let's think about the wave function. We have a wave function, and then apply a time evolution operator. So we simulate the time evolution wave function. And if this wave function is an eigenfunction of the Hamiltonian H, it causes just a phase shift depending on the energy without changing the structure of the wave function. So it means if we can determine the phase shift caused by time evolution, we can extract the energy eigenvalue of the system by using this expression. Okay, so this is a quantum circuit for the 1 qubit quantum phase estimation algorithm. And today I'm not going to talk about the detail of the quantum algorithm, but roughly speaking, this quantum gate generates the quantum superposition of 0 and 1 state, and then apply a time evolution operator. If this ancillary qubit is in 1 state, and then perform another Adamov operation and measure the quantum state. And if the evolution time here, t, equals 0, the measurement result is always 0 states. But if t becomes worse, for example, this time evolution operator changes the phase just 90 degrees, the measurement outcome becomes 1-to-1, 50-50 of the 0 and 1 state. If this time evolution operator will cause a minus sign, the measurement result becomes 1 state. So the probability of getting the 0 state can be calculated as shown here, which depends on the cosine function of the phi, which is an eigenphase of the Hamiltonian. So we can extend this quantum algorithm to n-qubit quantum phase estimation systems. In those cases, we can apply several Adamov operations to the n-qubit system, and then apply a control unitary operation. Here, unitary is a time evolution operator, and then measure the quantum states. If we apply this quantum n-qubit quantum phase estimation, we can obtain the eigenphase of n digit in binary. So basically, this quantum phase estimation can be understood by here. If the first qubit is 1 state, it means that Fuchsian energy or eigenphase is somewhere around here. If the second qubit is 0 state, the Fuchside energy should be somewhere around here, and so on. So it means quantum phase estimate algorithm calculate the energy range where the Fuchside solution locates rather than Fuchside energy itself. And importantly, to make the energy range to be half, we have to double the computation cost because the evolution time should be doubled to regal another digit. So let me, so of course, in order to perform this kind of quantum simulation, we have to map the wave function on the qubit. And there are several approaches for wave function mapping, but I used a very primitive one known as a Gauss mapping. In the Gauss mapping, each qubit has an occupation number of particular spin orbitals. So it means the qubit should be in one state if the spin orbital is occupied. And if the spin orbital are unoccupied, the qubit should be in zero states. So the hard fork wave function can be represented as shown here. And more complicated wave function like this kind of CI expansion. This wave function can be represented by a quantum superposition of several quantum states. And the question corresponds to the question of the basic case. But you know that electrons are fermions, so but the qubits are not fermions. So because of electron fermion, so a wave function should be anti-symmetrized. So it means that if we swap two electrons, the equals the minus sign. So in order to satisfy this anti-symmetric condition, the relation and annihilation operators were represented by a product of these Pauli operators. And X, Y, and Z are Pauli operators acting on the qubit in the subscript. So let me briefly summarize the quantum chemistry on quantum computers. The first CI calculation, which gives the variation-based particle wave function within the base set being used, the computational cost of the full CI is exponential against the system size on classical computers. But it becomes polynomial on quantum computers. But importantly, even if we use a quantum computer, we have to compute energy of high spin and low spin state individually to calculate the exchange parameter J. But let me rethink why the quantum computer is so powerful. Because quantum computers can utilize the quantum superposition state as a computation resource. So why don't we use the quantum superposition of high spin and low spin states to calculate the spin state energy gap J directly on quantum computers? This is the basic idea of the algorithm. And in order to perform such calculation, we developed a new quantum algorithm. So here we think about the two-spin system as a simplest example. But this quantum algorithm I will show you is valid for any number of spin systems, as long as the system is approximated by a two-side Heisenberg Hamiltonian. And let me think about two-spin systems. The spin singlet and to the state, and the energy gap is 2J, and we want to calculate this J bar. Instead of calculating this J bar directly, we think a cyclic Hamiltonian H dash, which is the sum of the original Hamiltonian and J x square operator. So under this cyclic Hamiltonian, the spin singlet state doesn't change the energy because of the eigenvalue of the x square operator or spin single state is 0. But spin triple state, the energy will change depending on J value. And the gradient of this curve is good. So two lines should intersect somewhere. And this energy gap is 2J and the gradient is 2. So it means the J value giving where the two lines correspond to the J value of the Heisenberg Hamiltonian. So the problem to calculate the spin state energy gap or exchange coupling parameter is equivalent to the problem to find the J parameter in the system Hamiltonian H gas, where the two spin states, in this case spin single and triple states, have the same eigenvalue of the H gas. And we can revise this problem as shown here. The problem to calculate the J parameter is equivalent to find the small J parameter, of which the wave function in superposition of high spin and low spin states becomes an eigenfunction H gas. Actually, the approximate wave function is a superposition of high spin and low spin states. So it means we can use this approximate wave function as this Poincare superposition. And if the approximate wave function is eigenfunction of the H gas, the time evolution of approximate wave function causes no change of the shape and just cause phase sequence. So it means we can evaluate the square overlap before and after the time evolution to estimate how the broken single wave function is close to the eigenfunction of H gas. Actually, there are no well known Poincare algorithms known as a swap test, which can evaluate the square overlap between two Poincare states. And this is a Poincare circuit for the swap test. And if we apply this Poincare circuit, the probability to obtain the zero state in the measurement of the first cube is calculated to be here. So the probability to obtain the zero state depends on the square overlap between two Poincare states, phi and psi. So we can utilize this Poincare algorithm to evaluate this square overlap. And this is the Poincare circuit for the Bayesian exchange coupling parameter calculator with Brook wave function. This is the name of the new Poincare algorithm. I abbreviate as a BFD. As you can see, there are two wave functions, Brook wave function, and one we apply the time evolution operator to one of the Brook wave function, and then apply a sub test. If the wave function can be approximated by a linear combination of high spin and low spin states, the probability to obtain the zero state in the measurement is calculated to be in this equation. So it depends if on the energy difference under the system Hamiltonian delta E gas and time evolution range. So we can sweep the J value to evaluate the P0. The P0 has an upward peak of J small j equals J. So we can optimize the J parameter by using machine learning techniques such as Bayesian and inference to optimize the J parameter, giving the largest probability of obtaining the zero state. And the algorithm is something like that. First, we set the Gaussian function as a prior distribution, and then perform several quantum simulations with different J values. In this case, in my algorithm, we apply 21 points between mu and sigma square of mu is the mean, and this sigma square is the variance of the Gaussian function. X is the quantum study as shown before 1,000 times. And the results become something like that. And we can fit this result by a Gaussian function. This corresponds to the regular function. And because the paradox addition and regular function, both of them are given by a Gaussian function, so we can calculate both distributions, which is the product of these two Gaussian functions. If the variance of this product distribution is smaller than threshold, if the algorithm becomes the mean mu as the estimate of the J value. So, but unfortunately, the quantum computer currently available is too noisy to obtain meaningful results. So we developed a quantum static simulation program using Python and perform numerical quantum simulation, quantum static simulation on classical computer. So I applied our algorithm to the hydrogen molecule at the Functionalization exclusive level. And the first step is something like that. The J should be between -1 to 1 Hartree. But if we perform machine learning by using Bayesian inference, at the step 8, the J value should be somewhere between -0.02 and -0.005 Hartree. If we apply this approach to covalent bond diffusion hydrogen molecules, that's because it's shown here, and black line is a Functionalization, and this open circle corresponds to the quantum static simulation by using quantum algorithm. And instead, this figure is the deviation of the J value from the Functionalization value. And as shown here, our quantum algorithm can calculate the J value within 0.5 kilocalories per mole. As I said, our quantum algorithm is applicable to any number of spins as long as the system is approximately 2-sided Hamiltonian. So I applied this approach to triple bond dissociation of nitrogen molecules, and result is shown here. Because the triple bond dissociation involves 6 electrons, so the possible spin state is singlet, triplet, and quintet, and septet states. And the energy gap should be 2J, 6J, 20J. And the result of the quantum static simulation is shown as a circle. And as you can see, our quantum algorithm can reproduce the J value very accurately, even for 6 electron species. And this algorithm can be applied to calculate the virtual ionization energy, because ionization changes the number of electrons to even number to odd number, or odd number to even number. So the eigenvalue of X bar operator is always different between neutral and cationic states. So we can apply virtual ionization energies. The result is shown here in this paper. Because I almost running out my presentation time, so let me summarize my talk. So we have proposed a new quantum algorithm named as a Bayesian exchange coupling parameter calculator with Brook symmetry function. And this quantum algorithm is capable of computing energy gap between 2 spin states directly, without inspecting the total energy of high spin and low spin states. Or quantum algorithm is applicable to systems with any number of electron spins, as long as the system can be approximated to side Heisenberg Hamiltonian. I didn't say in detail, but our quantum algorithm, the exponential speed is guaranteed and easier to implement on quantum devices than conventional quantum phase estimation algorithm. Our quantum algorithm also robust against gauge and measurement error and noises, and applicable to the calculation by ionization energies. So the results are published in these two papers. Thank you very much for your kind attention.
Thank you very much, Kenji. Very interesting. And I can accept one or two short questions. Valentin Novikov was the first.
Yeah, thank you. You mentioned at this last slide that algorithm is robust against noise and unidealities of gates. So I guess that your computations were assuming that you have ideal gates and qubits and absence of decoherence and the rest. So why you think this algorithm would be more robust to any quantum noise?
Yes, I also performed noisy quantum simulations for the Viacheslav ionization energies. And the reason why our quantum algorithm is robust is because our quantum algorithm calculates the range of where the two exchange coupling parameter J is located, rather than point estimate. So if noisy quantum circuit simulation cause this kind of plot to be flattened, but as long as we want to know which point is more more realistic for the two parameters. So that's why our quantum algorithm robust against the noise.
Okay, yeah, thank you.
Okay, thank you. I think it's very interesting, and yeah, we shall see how it develops further. Thank you very much, Kenji.
Thank you.
And let's move for the next talk. And the next talk will be given by Viacheslav Kuropatov from Nizhny Novgorod, from Razuvaev Institute of Organometallic Chemistry. He is going to talk on functionalization of o-Quinines, Bistability, and additional ordering possibilities. Please, Viacheslav.
Do you hear me?
Yes, and we even see you and your presentation.
Okay, thank you, Matvey, for your kind introduction. Good morning for all. Minasan konbanwa. Sumimasen konnichiwa. And for me, it's a great pleasure to be at this conference each time. To meet the colleagues, to see beautiful science. And today I'm going to talk about functionalization of o-Quinines, their coordination properties. It would be great to meet in Nizhny Novgorod, which celebrates 800th anniversary, and tomorrow the main celebration will begin. But coronavirus has crossed our plans. Maybe we will be meet in person someday next time. I think that is no need in this audience to explain the features of o-Quinines as ligand. But I should note that bistability is inherent in the very nature of this molecule. Quinines can change their redox state directly in the coordination sphere of metal. We are organic chemists and have some experience in the functionalization of o-Quinine molecules. Modification of core is useful if you need to adjust a redox potential or steric characteristics. Here you see only the small part of o-Quinines that have been synthesized in our laboratory. Today I am going to talk about o-Quinines equipped with an additional coordination sites and redox functionalities. All quinines which will be discussed today were prepared from through annulation of one free diethyl ring to 4 and 5 positions of o-Quinine core. Fused one free diethyl ring provides rigidity for the molecules, for the ligand molecule, and allows pi conjugation between o-Quinine and substituent which is placed in the two position of fused ring. We use quite a synthetic approach in the preparation of our compounds, and this approach is shown here. There are the topics that I am going to focus on today. And I'll begin with the orthoquinone with fused ditiate ring. It originates from such a species by decarbonylation of annulated ring. The unique feature of this compound is the fact that it combines both diethylene and dioxylene coordination sites. And these sites exist in the same oxidation states. Actually, one can imagine diethyl orthoquinone form for this molecule as a resonance form. Due to additional ring attached to the molecule, it has 5 oxidation states from 0 to -4. And here I shown possible chelating coordination modes for dioxylene and diethylene coordination sites. There are analogs exist in there are analogs that also combines diethylene and dioxylene coordination sites, but all they analogs corresponds only to diprotonated dianion species of our ligand. I'm going to discuss about coordination abilities of our ligand in different oxidation states, and I skip zero-valent state, and we'll begin from monoreduced species. According to EPR spectroscopy data, all these compounds, all these monoreduced species behave as typical semiquinones. Nonetheless, the ditiate site in such a species remains ready for other metal fragment addition. For instance, manganese carbonyl semiquinone can react with additional amount of demanganese decacarbonyl to give corresponding free nuclear species. Concerning two dianion form, for our ligand, there is a diversity in the direction of coordination. This differs is our species from our analogs, since structural database search reveals only a dithylate mode of coordination for mononuclear complexes with this ligand. There are a lot of factors influence on the direction of addition of metal fragment on complex, but in my mind, the most significant is Lewis acidity of the metal fragment. For example, in the series of platinum, palladium, and nickel phosphine complexes, platinum and palladium ones are dithylate, and nickel becomes catechylate. Lewis acidity could be also adjusted by the modifications of auxiliary ligand. If for copper-2 TMEDA complex, catechylate state is characteristic both for solid and for existing in solution. If we change TMEDA with a more soft base by pyridine or orthophenantraline, the compound remains catechylate in solid form, but in solution it exhibits an equilibrium between catechylate and dithiolate forms. This equilibrium is easily observable by epiascot spectroscopy and by UV visible spectroscopy. The signal, corresponding signal, consists of superposition of two signals, which differs by G factor and hyperfine splitting constants.
Oh, Viacheslav, we lost you.
Metal ion from the anion to 1 1/3 average for free atoms here. We also result in the reversal of the coordination mode from the catechylate to dithiolate. This free nuclear compounds is promising in my mind, since the linear copper chain, this chain could be continued by adding of corresponding amounts of copper and ligand, and who knows what magnetic properties it will show. Here I shown how the change in the valence state of dithiolate containing ligand can result in transformation of binding mode. This is complex without any additional ligands. It is bis semiquinonate copper with dioxylin coordination mode, and this complex with diazodine exhibit a dithiolane coordination mode of ligand to divalent copper. And I'm going to the second part of my presentation. It's quite short part. Our synthetic approach allows to assemble by a quite simple way acceptor-donor-acceptor triads consisting of two quinones and tetratia full valent or extended tetratia full valent. I already reported this species previously. The most interesting feature of such a compound is a narrow gap between frontier orbitals. The results shown at this slide were obtained in our fruitful collaboration with a group of Fabrice Pointier. It was found that switching in the redox state of the ligand is accompanied by significant change in the magnetic properties of the molecule. In other words, the redox state of a ligand control SMM properties of whole molecule. And I'm going to the final part, which will be devoted to functionalization of orthoquinones with additional coordination sites. Using this approach, we can attach different functionalities to orthoquinone core, such as a simple carbonyl group or ionogenic groups and others and others. Such functionalities could be very useful, for instance, for organization of ordering in the crystal phase, like in this case, where the intermolecular interaction is organized through the coordination of peripheral carbonyl group to the metal ion of neighboring molecule. This complex exhibits a nice ferromagnetic ordering at helium temperature in a crystal phase. This is another example of functionalization of orthoquinone. We can attach a tritiocarbonate moiety or dinitrile species as here. For us, challenging was to combine orthoquinone with beta-diketonate functionalities in one molecule. It is an example. Surprising that in this reaction, we obtained also such a species which contain a first example of stable monotoid compound. Obviously, that this toid species also bears both orthoquinone and beta-decatenate functionalities. Our synthetic approach is quite versatile, and we can attach, for example, paraquinone metide, or even the meat fragments to the molecule. This is a variety of compounds prepared by this way. And for us, is significant how this species could act as a channel for electronic communications between metal fragments that could be bond and different sides of the molecule. In this case, study of spin density delocalization character for mono-reduced semiquinone derivatives is very indicative. And actually, for dinitrile species, spin density exhibit delocalization. We can observe splitting of unpaired electrons on the nitrogen of the peripheral group. The same situation was observed for paraquinone metide species, which display a delocalization of spin density to the attached fragment, and for beta-decatenate species, where we can observe splitting on these methyl groups. The localization of spin density was found even in case of toid species, where beta-decatenate fragment is situated perpendicular to the orthoquinone ring. And this is my conclusions. Finally, I should say that we succeeded in preparing Sergey Norkov, Konstantin Martyanov, Anna Cherkasova. And I am very grateful to Fabrice Pointier for our fruitful collaboration, and you for your kind attention. Thank you.
Thank you very much, Viacheslav, and also for keeping it exactly on time. We have a chance to ask questions. Please. Artyom Bogomyakov, please.
Hello, everyone. I would ask a short question about on slide number 8. You show a different oxidation form of the semiquinone. Number 8.
Yes.
Yes, this one. So you can draw the neutral form and 2- form in biradical state. Is it possible to stabilize a biradical state for neutral or 2- forms?
We just not seen an examples of such spin distribution. Maybe, but I think it will be difficult for such a small molecule.
Maybe try to calculate how far the biradical form is located. Is it thermally distinguished or not?
Okay, good idea. We will try.
Okay, thank you.
Any other questions? May I ask a very short question? You've shown beautiful simulations of EPR spectra, quite busy EPR spectra. Just, I'm curious, is every spectrum like that obtained with the unique set of parameters, or you have some, possibility to not even this one maybe a couple of slides before, there was, oh yeah, this one on the top. I mean, can you simulate it with a unique set of parameters, or maybe there is something, some uncertainty?
We vary line width or constants, and only through API Symphonia software.
Yeah, then it's probably unique. Yeah. Thank you very much, Viacheslav. Thanks for your nice presentation. And we move to the next one, to the last one in this section. And it's my pleasure to introduce Sergey Veber from International Tomography Center, who is going to talk on spin dynamics in vanadium complex under terahertz radiation. Please, Sergey, the screen is yours.
Thank you very much, Mr. Chairman. In this talk, I would like to tell you about the influence of high-power terahertz radiation to spin dynamics of VO-TPP sample. And by this way, we would like to study spin-phonon coupling. This work was done in collaboration with Institute of Nuclear Physics and with University of Florence. So in my talk, I will tell you about previous research of VO-TPP and spin-phonon coupling in these compounds. A few words I will say about the instrument we use to produce high-power terahertz radiation, and the method we use is time-resolved EPR. So I will say a few some details which will be needed to understand the results. As was already shown on this conference, vanadium complexes are considered as molecular qubits due to quite long spin lattice and spin relaxation times. And in these papers, it was studied the correlation between spin relaxation properties and vibrational bands, in order to understand whether it's possible to use chemical engineering to further improve the spin relaxation times by changing the phonon spectrum and spin-phonon interaction in these compounds. So in our research, we used VO-TPP sample, which stands for oxvanadium tetraphenylporphyrin, and we use it as a powder and we press it into the pellets. And two types of samples was used. So first one is 100 VO-TPP, magnetically concentrated one, which is a fast relaxing sample, so you are not able to observe any to do any pulse experiments with it. And another one is magnetically diluted, only 2% of VO-TPP, while the rest one is diamagnetic, is a structural matrix. And this compound shows quite slow spin relaxation time and is suitable for to be considered as a qubit. And in the papers I mentioned above, the spin lattice and spin memory time of this compound was studied. So it mentioned here by blue curves, and you can see a banding of T1 relaxation time at a temperature around 20 and 30 K. And also the samples was studied by far infrared spectroscopy, terahertz spectroscopy, and it was mentioned that there is a vibrational band at roughly 67 wave numbers. And so this behavior was simulated by behavior of temperature dependent of spin lattice relaxation time was simulated by different models, and one of them was considering direct process and a process associated with local vibrational modes. And in this model, it was shown that this behavior can be nicely simulated, assuming the vibrational band, which is experimentally observed. And thus, this compound is a good candidate to further study of spin-phonon interaction. And this results was later strongly supported by theoretical consideration done by Alessandro Luni and co-workers. So how to study the spin-phonon interaction process? Basically, we can use to pump. We should pump phonons and probe the spin dynamic. To pump phonons, we use a free electron laser, which is able to produce up to 100 watt at the frequency of our interest. So here you can see far infrared spectra of VOTPP, and this is the band which we would like to pump. And also free electron lasers are able to tune the frequency. So it's a good feature of this instrument. It means that we can not only pump the top of the vibrational band, but also walk around it, as I will show you later. In our experiments, we use terahertz pulse with the length of 350 or 700 microseconds, and the power which we used was in the range from 10 to 100 watts. So about EPR, so we use X-band EPR spectrometer, which operates in the range of 10 gigahertz, and in two modes, CW EPR and time resolve, which we are interested in. So this slide shows how we fed the radiation to the sample. So we use a commercially available resonator made by Brook, and we use a special waveguide, and we feed the radiation to this waveguide. And also you can see here the sample, which is in a plastic container. We attached this plastic container to the waveguide and put it into the dielectric ring of the resonator. So this is the way we radiate the sample. On this slide, you see CW EPR spectra of VOTPP, which is obtained in the following way. So we just change the magnetic field and record the derivative of spin system absorption. So I guess many of you are familiar with this technique. And it's a typical spectra of magnetically diluted VOTPP. Everything is known about it. I mean, G tensor and hyperfine splittings. In time resolved technique, which we use, the procedure, experimental procedure is different. So we stay at the fixed magnetic field. At some moment, we perturbate our system, in our case by terahertz light, yeah, and we record the trace by fast digitizer, yeah. Then we change the magnetic field, repeat this sequence, and in this way we can measure 2D plot. And if we take two cross sections, one of the cross sections of time cross section will give us a spectrum, yeah, and you can see that it's correlate quite well with CW1, and the time cross section will give us a kinetic. So further, I will pay attention to the kinetic of the spectrum, and we will use the field position which correspond to the maximum of the spectrum. So all these lines behave in a similar way, but this one has the highest signal to noise ratio, which is important for us. So let's consider what is going on when we apply high power terahertz pulse to the sample. In our experiments, all the time we radiate the sample with the microwave. So then we apply the terahertz pulse, which is 350 microseconds. And as you can expect, it will change the temperature of the sample. So the radiation is quite powerful. It's absorbed by the sample, and sample is heated by the radiation. And if you look at the time resolved signal of the fast relaxing spin system, we will see at the same time we will see the negative decay. It means that when the temperature rise, the spin system less absorbing. Yeah, so it means that we will see the negative step, and then we will see how this signal will return back with the temperature, with the time of thermal relaxation. In the case of slow relaxing spin system, spins are not able to follow the temperature of the thermal bath, and we will see such a smooth change, and later again we will see the cooling. And this curve in our case, TF, can be simulated by TF, and it results of spin lattice relaxation time, and also the interaction of spins with the microwave power we apply. And so a general conclusion is that a fast relaxant spin system follow the temperature of the sample, while a slow relaxant spin system is limited. The dynamic of the system is limited by spin relaxation times. And here you can see the experimental data. So this plots show the same data, but in the different windows. Here we have almost 200 milliseconds, while here only 10 milliseconds. Yeah, and on this plot you mainly see the temperature relaxation of the sample, and you can see that for both magnetically diluted and magnetically concentrated sample, thermal relaxation is the same, and we will not consider this process later, so it is not interesting for us. But we will focus on the beginning of this kinetics, and here you can see that in the case of fast relaxant spin system, it follows the temperature of the sample as we expected, and then relax. And in the case of magnetically diluted sample, we see that the system is not able to react to the heating of the sample and do it very slow. So here, just an example of real experiment with magnetically concentrated VOTPP sample. You can see the kinetic as a function of microwave power applied. So very low microwave power to quite high microwave power. You can see that nothing is changed except that we improve a signal to noise ratio when we increase the microwave power. Yeah, so no saturation effect, and all the time spin system is able to follow the temperature of the sample. So, but in the case of slow relaxing spin system, situation will be different. Let's consider it using theoretically, I would say, with numerical calculation using modified Bloch equation, what we consider in this model. So we know that we apply 0 Hz pulse. It means that the temperature of the sample will be changed, so we take it into account. And it also means that the T1 of the sample is time dependent in our experiment, since the temperature of the sample is changed. And the temperature dependence of T1 is also well known. We measured it by pulse CPI technique. And so when we apply very low microwave power, we do not saturate the spin system. And in this case, when we hit the sample, it will react. So we see very slow change from one level to another, and the relaxation time is about T1. Also, when we further apply higher power, it will be almost the same till the level when we start to saturate slightly the sample. We will see that this transition area becomes faster. And at the moment when we saturate the sample by microwave power, we will get a positive kinetic, and by changing the increasing power further, the slope will be shorter and shorter, and finally it will show clearly us the time we applied 0 Hz pulse. So the spin system will follow the temperature of the sample just because of the very high microwave power, which induce a lot of spin transition in the system. But nevertheless, it's quite difficult, quite not trivial behavior. But what I would like to stress, it's in all the cases we see monotonic change of the signal between these two plates. Yeah, it could be, so it's important for us. And on this slide, you see the results of experiment we performed. In the beginning, I would like to pay your attention to the difference we observe between simulations and experimental data. For example, if we these three curves look similar, but if we overlap them and make a zoom in this area of the terahertz pulse, we will see that before the black one goes down, it tries to go up. Yeah, and also further, you can see some kind of overshooting, which we did not observe in the simulations. And quite strong effects that we expected caused by temperature, by the heating of the sample, and we can partially subtract this effect. For example, we subtract from the third curve, from the third one, the green one, and in this way we neglect the temperature effects, and we'll clearly see the effects of terahertz light. You can see that during the pulse we have a quite linear increase of the signal, which means that the system relaxes within the terahertz pulse, and then we see the decay which take place with the time of spin lattice relaxation time. So it means that this is not a temperature effect, but a real effect of spin relaxation, and then this when terahertz pulse is off, the relaxation returns back to the system. So and in order to simulate these experimental results, we would like to include into consider it above Bloch equation a phenomenological relaxation process. Yeah, so we do not tell here about the relaxation mechanism, but just assume that when the terahertz pulse is applied, the relaxation of the system is faster. So you can see it. Yeah, and actually it was enough to get all these overshoot effects, and you can clearly see here these steps, and also this this line, which is also simulated and quite nicely represents this one. And according to this simulation, we can conclude about the efficiency of terahertz relaxation processes. So we have some uncertainties with determination of temperature jump, and taking into account these uncertainties, we estimate the time of terahertz relaxation in the range of 30 to 300 milliseconds. It is also interesting to look what is going on when we change the power. Here you can see that if we increase the microwave power from almost 10 watt to 100 watt, we increase the intensity of this positive feature observed in the spectra. Here you can see the kinetics, and in general we can describe it by linear function, which indicates the single phonon or single photon nature of terahertz induced relaxation processes. And another type of experiments also I would like to show you is a sweeping of the terahertz frequency. So here you can see the vibrational band of VOTPP, and these curves show the energy spectrum of terahertz light we applied. So we sweep this vibrational band, and here you can see the kinetics we measured at the maximum of the spectra. Clearly, when we out of the resonance, the signal becomes much smaller. When we on the line, we observe the effect much stronger, and this is the maximum of the amplitude, and you can see it correlates well with the vibrational band. So I would like to conclude this first result that in principle, I hope I convinced you that terahertz pump PPR probe technique is suitable to study spin-phonon interaction in such type of systems, that irradiation of VOTPP at the vibrational band frequency results in terahertz-induced acceleration of spin relaxation. And we observe that this relaxation time is about 10 to 100 milliseconds, and the power range we used. Most probably, it is single photon or single phonon nature of terahertz induced relaxation. And it is also a clear difference between two cases when we in resonance and or off resonance when pumping the vibrational band. And for us outlook, I would like to tell you our future plans. So Andrea Albina from Florence University did a first principle spin dynamic simulation of this system. The red one is a theoretical obtained absorption spectrum. The black one is experimental one. And here you can see Spin-Phonon intensity coefficients of vibrational of this vibrational band. So as I told you, we studied this vibrational band, which is quite small in intensity, and you can see that also Spin-Phonon coefficients is also quite small. And also Novosibirsk electron laser allows us to study this one, also vibrational band, which is much stronger first of all, and then it has much higher Spin-Phonon interaction. So we hope that so at least the theory predicts more efficient vibrational bands, and we hope to study it in the near future. I would like to thank my colleague from International Tomography Center, colleague from Institute of Nuclear Physics who help us with Sergey's radiation, and team from Italy, Stefano Benci, who spent several weeks in Novosibirsk doing together with us this experiments, Fabio Santani, who synthesized these complexes, Andrea Albina, who did this theoretical consideration, Renata Torre, who is a specialist in terahertz CPR spectroscopy, and Roberto Cessali, with whom we discussed this project and planned these experiments. And thank you very much for your kind attention.
Thank you, Sergey. So we have time for a couple of short questions before the break. Valentin Novikov, please.
Yeah, very nice progress. So you are going to go from the line where you have sizable spin-phonon coupling to the line where you have strong spin-phonon coupling. But what if you go to the opposite way? What if you choose some phonon adsorption which has no spin-phonon coupling whatsoever? So it shouldn't, in principle, lead to relaxation. And should there? So will you still see some changes in relaxation? Because you will hit the sample, but how it will impact the relaxation?
Yeah, so it's very interesting question. There are several possibilities. We can change and we can choose another vibrational band, or we can choose a transparent area, for example. And I cannot, in principle, we should, according to theoretical consideration, to our expectation, we still should have, in the case you suggest, we still should observe, of course, this temperature-induced effects, while the acceleration of relaxation should be much smaller. Yeah, but we should check this. So we did not, we have no experimental results about it yet.
Okay.
And Matvey, I also see that Boris Zuckerblatt would like to ask.
I don't see that. Why? Well,
yeah.
Yes, Boris, please ask a question.
Sergey, first, thank you very much, because your talk was absolutely interesting and new in this area. I like it very, very much. I have one question. You assume that you introduce to the system terahertz frequency. Are you sure that when you introduce this frequency, you produce heat, or the phonon or the vibration that are created by this terahertz radiation are in thermodynamic equilibrium with the vibration of the system? Should I understand this is the only heat, or this is something non-equilibrium in the system? Because this is an important question for the mechanism of relaxation. because the relaxation can be induced only by the thermodynamical equilibrium, by heat, by the continuous spectra of excitation, rather than the local the vibrations that have discrete spectrum.
Very deep question, I would say, and I'm not sure I will answer now. Actually, on this slide, you can see that I wrote both single photon or single phonon nature. Yeah, so it means that we have no direct conclusion about it now. But in principle, we irradiate our sample with photons. Yeah, and there are two possible ways to interact. The spin system can interact with it. First of all, the photon is absorbed by vibrational band, so then the system will be excited, vibrationally excited. For how much time, it's unclear. Probably it's very short time. Yeah, and it seems that we are not able to change, I would say, the temperature of exact vibrational band. So because there is vibrational relaxation time is very fast. But another possibility to interact is a direct interaction with electromagnetic wave also. So but then it also could be the interaction of spin system with high power terahertz radiation without phonons, I would say. Yeah, so this mechanism is unclear yet, and also additional experiments will give us insight about it. So the experiments which proposed by Valentin, for example, the experiment which when we irradiate the sample at the transparent area of the spectrum, yeah, and the experiment which I proposed in the end of my talk, when we excite the vibrational band which with much more stronger spin-phonon interaction. So if we talk about experimental data, we are not able yet to conclude on your question.
Thank you very much. Thank you very much. Let me thank you again for your very, very nice presentation. Very interesting, physically interesting. Thank you.
Yeah, yeah. I suggest we have something like 15 minutes break, and then we get back. But Sergey, there was a question to you from Efa in the chat. Would you please answer it, and we can also read it all as well.
Okay.
Okay. Let me thank all presenters of this section, and let's get back in 15 minutes. Thank you.